In this video, we're going to talk about gas laws and chemical reactions. So I know topic 5 is a little bit of a mishmash of biofuels and gas laws, but we are going to gloss over gas laws. But what I really want you to take away from this is how gases interact, and we're also going to talk about using mole ratios in gas law calculations. So that's going to kind of help tie this in together here. So let's talk about what a gas is. So gases are used and created in chemical reactions a lot of times. We see them produced in combustion reactions like our CO2. Our H2O also is a gas. It's actually a water vapor whenever you have a combustion reaction. And these gases are still molecules. So we have our liquid molecules, and they get converted into our gas state. They're still the same substance. If you go from a liquid or a gas, but it turns into a different phase. It has a phase change. We've talked about these. So we produce these a lot in chemical reactions like this one right here. You've probably seen gases in a lot of applications. We see them used in things like propane tanks, again, combustion reactions, car engines, also combustion reactions. You see gases for applications like in your car tires. This is really important. Medical oxygen tanks. We also use gases for diving tanks. Anytime you see a tank of some sort, it usually contains a gas, and these can be produced via chemical reactions or used via chemical reactions. Let's look at what a gas is before we dig too much into this. So something that's unique about a gas is that a gas doesn't have a definitive shape or volume. So we actually have to hold it in a closed container, right? Because it will just disperse out if we don't. It uniformly fills any container that it's in. It will just disperse outwards. And because of this dispersion process, it exerts pressure on its surroundings. So think about the car tire example. If you have air in the car tire, it's going to put pressure in your tires. And that's because of the gas molecules inside of it. Gases also change volume, i.e. how much space they occupy, with temperature and pressure. So as you heat them up, they're going to change their volume. As you change the pressure, they will also change their volume. And then the other thing to know is that gases are much less dense than solids and liquids, like way, way, way less dense. So remember that density is mass over volume. So that means in any given volume, so in a space, there's going to be less mass if you have a gas versus if you have a solid or a liquid. I always like to visualize it as kind of our atoms or molecules in a space. So if you had a solid, they're going to be really close together, kind of like this. If you have a liquid, they're going to space a little further apart, kind of like this. And if you have a gas, they're going to fill their container, so they're going to go even further apart. So you might have something kind of like this for a gas. They're much further apart, which is why they're less dense, because there's less mass in that area per the volume that you're investigating or looking at. Let's take a look at our mole ratio. So ignore this term right here. So mole ratio in calculations. Okay. So here's a chemical reaction, this one right here, that's actually used in airplanes. So whenever you're in an airplane, they show you how to use like the oxygen mask. This is how they actually make the oxygen. It's made via chemical reaction. They mix this sodium chlorate chemical here. It's a solid, and they mix it with an iron solid. And it goes through this cool chemical reaction where it makes oxygen gas. Awesome. And some other byproducts. So this gas is something that you breathe in whenever the emergency oxygen mask comes on. Okay, so the question is here, say you need to have so much oxygen on board your plane. How much of this stuff should you have on the plane in order to make sure that you can produce enough gas? Okay, so it asks you here how many grams of NaClO3, we're looking for grams of this, are needed in a typical generator to produce 125 liters of oxygen gas. Okay, so remember they're in containers normally, so you'd have like 125 liter of oxygen gas. So it's asking us how many grams do we need to get here? And it also gives us some other values, pressure and temperature. So if we think about last time we did a unit conversion with mole ratio reactions. We would look at the equation above and see that, well, for every 1 molecule of our sodium chlorate, there is, 1 mole of our oxygen gas. This is a balanced chemical reaction that you're seeing here. So we see our mole ratio here. So you might think, okay, great. So we're going to take this NaClO3 number, grams. We're going to take that to moles of NaClO3. We'll use our mole ratio here and get that into moles of O2. Straightforward enough, right? But then normally the last thing that you do is you go to grams from here, right? And you find grams. Well, it's not asking for grams because you can't really measure a gas in grams. Like a gas it's all floaty and you can't put it on a balance. Like you can't put it there and measure it. So we measure it in volume instead. So we've got this volume. So we don't go to grams, we have to go to liters. So from moles, we have to go to liters. So this is, so in between here, this translation process, this is what we're missing. And we need a way to be able to do this conversion. So we're going to learn how to do this. All right. So if you want to know how many moles of oxygen are in a specific volume, because this is how we measure gases. We measure gases in volumes. We're going to need some more information. So we're going to learn about how gases behave and how we can relate these behaviors. In order to do this, we use something called the ideal gas law. So the ideal gas law relates the pressure, the volume, the number of moles, and the temperature all together of a gas. So inside this equation, PV equals nRT. You will probably need to memorize this because you will see it on the exam. Let's learn what all these variables are. So this is pressure here. Okay. And it's going to be in a unit called ATM. So we usually refer to that as like atmospheres. Volume is here. This is our volume. This is going to be in liters specifically in our equation. N, I know it's a little confusing, is moles. It should be M, right? But we write it as N. So N is number of moles. So that's here in our equation. And then T is temperature. Awesome. Please note that it is in Kelvin. It's not in Celsius like we normally use in chemistry. It is in Kelvin. So that's our temperature in here. Okay. And then we have this thing called R. R is our universal gas constant. So it's a constant number that was calculated that relates all of these variables to each other. It allows us to compare pressure, volume, and temperature and number of moles to each other. And it's just a standard number, okay? So you're going to need to also memorize this as well. You'll be using it a lot. Here's the value for R. That's just R. It is 0.8206 liters times atmospheres divided by Kelvin times moles. So it's got this weird unit on it here. The reason it has that unit is because everything else in your ideal gas equation has these units. It's got ATMs in it, liters, moles, and Kelvin. So understandably, those are the units that appear in our ideal gas constant because we need them to cancel out. So we're going to use our PV equals nRT equation to help us measure gases because we can't measure them on a balance. We can't measure their weight. So we're going to use this equation instead. So let's take a look here at our original problem that we had looked at. We were trying to find out how many grams of sodium chlorate are needed in a typical generator to produce 125 liters of O2 gas at these temperature and pressure conditions. So in order to find this grams here, remember we needed moles. We're going to go to our mole ratio, moles of NaClO3. We're going to use our mole ratio here to get to our other substance, which is O2 moles. And then from there, we're going to go to liters, 125 liters. Okay, so this is how we're going to find this. Okay. So we're given 125 liters of oxygen gas and we want to find grams, so we're going to go the other way. We're going to be going backwards, okay? So let's start with this 125 liters value. And we want to find how many moles this is. We need moles of O2. So we're going to use our PV equals nRT equation. So we can put our volume in, our 125 liters. This equation also gives us some other information. It gives us our pressure in ATM. It gives us our temperature in Celsius. Remember, we need it in Kelvin. So we've got to get to Kelvin first. So 20C plus 273 equals our Kelvin value. So 293 Kelvin. So that's our temperature. And we know our gas constant because that's a standard number that never changes. It's always the same thing. So this is 0.082, I believe. So that allows us to get to moles. So we can literally just plug all these numbers in. 1 ATM times our volume, 125 liters. We're solving for moles. This is going to be over our R. 0.082, keep writing this backwards, times our 293 Kelvin. This will give us moles of O2, which we can then use our mole ratio in order to get to our sodium chlorate values. So this is how this equation comes in handy and how we can incorporate it with our mole ratio. Let's take a look at another more basic problem to help you get the hang of this math. So I'm going to let you work this one. So calculate the pressure in ATM of 1.2 moles of methane gas in a 3.3 liter container at 25 degrees Celsius. Use your PV equals nRT equation. Now remember that this value here is 0.082 ATM times liters over Kelvin times moles. Okay, so go ahead and pause the video and see if you can solve this one on your own. Let's take a look at how to find pressure using our ideal gas law. So if P is unknown, we're going to leave it as a variable. Our volume is 3.3 liters. It's in the right unit because it matches the unit on our ideal gas constant. All right. Moles, we have 1.2 moles. This is the correct unit because it matches our ideal gas constant. So we know it's going to cancel out at the end of the day whenever we do this math. We're going to multiply that by our ideal gas constant, 82 ATM times liters per Kelvin times mole. And then we have our temperature. Temperature is not in the right unit. It's in Celsius. We need it to be in Kelvin. So we're going to go ahead and convert before we put it into our equation. 25 Celsius plus 273 is going to give you 298 Kelvin. So that value will go right in here, Kelvin. And now you can solve for pressure. So because this is multiplied by pressure on this side, in order to undo it, we're going to divide both sides by 3.3 liters. Divide this side by 3.3 liters. It's going to get rid of it here. And now what we can see is that all of our units cancel out. Liters cancels with liters, moles cancels with moles, Kelvin cancels with Kelvin, to leave us with ATM. So our final answer here is going to be in atmospheres. So let's find out what that value is in our calculator by doing 1.2 times 0.082 times 298 divided by 3.3. So what you end up with here is that your pressure is equal to 8.9 atms. So that's how you would solve this using the ideal gas law equation. Now keep in mind we've done an example with pressure and with moles. Any of these numbers in your ideal gas law equation can be unknown. So you could have an unknown volume. You could be solving for volume and be given pressure, moles, your gas constant, and temperature. You could be solving for temperature and given all the other ones, your pressure, volume, moles, and your gas constant. They could even ask you to solve for your gas constant and give you pressure, volume, moles, and temperature. So keep in mind that this is a flexible equation that's going to let you relate all of these variables because they all affect how your gas interacts with the environment around it. Let's take a look at how gases change when these forces on them change. So pressure and volume are related in a gas. So if we think about pressure as maybe a confined container, I always like to think about that. So inside of both of these containers, we have the same amount of molecules. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Same exact number of moles. But when you take this container and you make it smaller, i.e. you have a smaller volume, so volume goes down, all right? We look at our pressure here. We've got a much higher pressure than our initial one. So when volume goes down, pressure goes up, which makes sense if you have something that's bouncing around and all of a sudden you compress it and now it's got a smaller space to bounce around in. The amount of times it's hitting the walls is going to increase, and that's going to increase the pressure. Pressure is determined by the molecules hitting the walls of the container. So the more collisions you have on the side of the container, the higher the pressure. Let's talk about how moles of a gas and volume interact. So moles, you can visualize it as, again, these are your little gas molecules. So say in this balloon we've got 1, 2, 3, 4 moles. And let's say we put more moles in this other balloon, 1, 2, 3, 4, 5, 6. As you put more moles, more gas into a space, the volume is going to increase. And we can see that by the simple act of blowing up a balloon. As you put more air into it, it gets bigger. Temperature and volume also change with gases. So as you increase the temperature of a gas, its molecules move faster, okay? So a gas moves more quickly when you put more energy into it and you heat it up. That's just what happens. They can move faster. And we can see that here in this diagram at this temperature. This is really cold. We're seeing this is our molecular speed. As it gets to room temperature, this is our average molecular speed. It's going up. And as we get here to 600 Celsius, that's quite hot, we've got a much higher average molecular speed. So here, here, and here. So it's getting faster and faster and faster as we heat things up. And so this is going to affect our volume. If our molecules are moving faster, they're hitting the walls more frequently because they're zipping around as opposed to really slowly going. And so this is actually going to expand your container. So again, a balloon example is really great. A balloon's a really good visualization for these gas laws. So think about if you take a balloon and you put it in a hot area. So you have a closed balloon, right? You tie off the end, you blow up a balloon, you tie the end, you put it in a hot area. It's going to expand. If you take that same balloon and you put it, say, in your freezer, it's going to shrink. And that's because of this temperature change and the way the gas molecules are hitting the sides of the container. On that note, we see a similar effect between temperature and pressure. So think about your tires in your car. So one good piece of advice is that when it's cold outside, you should always inflate your tires because as your temperature goes down, pressure also goes down because of these gas molecules. So if your gas molecules are moving around and all of a sudden you make them cold, they aren't moving as much, they're going a lot slower. When that happens, they're going to be hitting the walls a lot less. So they might hit once. The frequency that this happens is going to be a lot less. Whereas if it's a really high speed, they might zip, 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 zip. And the collisions with the wall are what is causing that pressure increase. So collisions with wall, container, wall, are related to pressure. So it's very important that you inflate your tires in cold weather because the pressure is naturally going to drop in them. Here's another way to kind of visualize it if this helps you at all. So here's one temperature and here's the temperature 3 times higher. We can see that these molecules are moving a lot less. Their directional arrows are much smaller. These are much bigger arrows, so they're moving further. And you can see here that this is a weight. So in order for this lid to stay on, we only need 1 weight in the first one. But then in the second one, as the temperature gets 3 times higher, we need 3 weights to keep it down. So we need more weight to keep that there because there's more pressure. Otherwise, it would be an expanded container. So in order to keep the volume constant, we've got to have something to keep that under control, and we need more there because there's an increased pressure. So in this class, we're only going to work in ATMs. We aren't going to be worrying about any of these other conversions like pascals, kilopascals, or like in your tires, PSIs. We aren't going to be doing that. It's just going to be ATMs. You'll be given these values. So if you remember this from another chemistry class, the good news is you don't need to know it for this one. Okay, now I just want to go back to this last example here, and I want to work this problem to the end so that you can see one of these problems worked out fully. So we have already found the moles of oxygen in the container using our ideal gas law. This value comes out to be 5.2 moles of O2. Now our question asks us about grams of sodium chlorate. So we're going to need to take this to our mole ratio in order to get to the new substance. So whenever you're changing substances, you have to use our mole ratio. Because we're going from O2 to sodium chlorate, we've got to use our mole ratio. So we're going to go ahead and do this. So if we have 5.2 moles of O2, we're going to want to convert. So for every 1 mole of O2, we have 1 mole of sodium chlorate. Simple enough. Okay, so this gives us moles of sodium chlorate. So we end up with 5.2 moles of sodium chlorate. And now we want to know how many grams, so we're going to use the mass from our periodic table in order to do this. So we're going to need to go to the periodic table and add all of this up. 1 sodium plus 1 chlorine plus 3 oxygens. And what we find is that our molar mass after that is 106.44 grams per mole. 106.44. So you can just plug this into your calculator and find the solution. So we find that we need 553.8 grams of sodium chlorate. So this problem is a combination of our ideal gas law and our mole ratio. You'll see examples like this on the homework to help you solidify this concept.